Hello and welcome to part one of a three-part lecture series on this chapter. It's chapter 5 from the text that we refer to occasionally on microbial metabolism. It says microbial, but this will be basic metabolism. Microbial or eukaryotic metabolism, it'll work pretty much the same way for all forms of life. There are a few differences between them, and we'll discuss those. But overall, the basic process remains the same in both prokaryotic cells and eukaryotic cells. Of course, there are differences such as having mitochondria or not having mitochondria, but we'll discuss those as we go through this chapter. So let's begin. So these three terms, the bolisms, I like to call them. Metabolism is the sum of all of the chemical reactions in an organism. Catabolism is the energy releasing or the exergonic reaction. So this is breaking down. Organic compounds are broken down, their bonds are broken, and when bonds break, energy gets released. And so that's why these are exergonic reactions, because these covalent bonds that are holding these atoms together, those bonds will break. Almost always through the use of enzymes, but not always, but almost always, and then energy gets released, and then that energy is used to drive reactions within cells. Anabolism is the energy using side of it, that's endergonic, and so this absorbs energy, and so energy is put into these smaller constituent compounds, and that energy then is stored up in these larger organic compounds within cells. So catabolism is energy releasing, anabolism is energy using or energy absorbing, and then you take those two together, catabolism and anabolism, and you get the sum of those. We call that our metabolism. So it's the rate at which the chemical reactions occur, both building up chemical reactions, the catabolic reactions, and breaking down the building up the anabolic reactions or the breaking down reactions. Those are the catabolic reactions. So catabolism plus anabolism equals metabolism. So this graphic here, it's circular, it's cyclical, and so you can jump in anywhere in there, and you can see how it's a basic cycle that goes on within our cells in order to break down compounds or to build them up. So if we start at the top in the middle, the simple molecules such as the building blocks, they're glucose, amino acids, glycerols, fatty acids. We start with those and we go in a clockwise direction. Anabolic reactions transfer energy from ATP to complex molecules. So the energy is given up by ATP into these simple molecules, and then the simple molecules then join together, heat gets released, and so complex molecules then are built up, such as starches and proteins and lipids. So remember, these are endergonic reactions. They're absorbing energy. Where is the energy coming from? It's coming from ATP. So the energy leaves the ATP, goes into these simple molecules, and then larger, more complex molecules such as starches and proteins and lipids are built up. We keep going there. Catabolic reactions transfer energy from the complex molecules to the ATP. So the energy leaves those complex molecules, goes into the energy molecule ATP, and ATP then has energy. It has been energized, and heat is released again. So we can keep going around and around and around. The complex molecules are broken down into their simple molecules and so on. So this process is continuous within cells. This is how cells extract energy from compounds or they deposit energy into compounds. And it just keeps going around and around and around. This is our metabolism. So as you see at the top, the catabolism provides the building blocks and energy then that's needed for anabolism, so that these compounds then can be built up. We'll be discussing some pathways or metabolic pathways. Well, what is a pathway? It's a sequence of chemical reactions that occur within a cell. So these pathways are step-by-step processes. They're usually a cascade type of process or domino effect type of thing. These analogies are used. But it's a step-by-step process that once the first step is accomplished, then the next steps will inevitably follow. Metabolic pathways are determined by enzymes. Enzymes are proteins, and they're determined by genes. And so this kind of shows how your metabolism is related to your genes, your genetic makeup. Because the enzyme function and enzymatic function and the way that they break things down and build things up, those are determined The enzymes themselves are determined by our genes, and as you know, DNA contains the instructions for making nothing except really proteins, and enzymes are proteins, and so therefore they're determined by our genes. And enzymes, and we'll talk quite a bit about them, that the suffix of enzymes, most of them, it's not all of them, is ASE. So you have, for example, there's a disaccharide called lactose that is found in dairy products. Well, we possess an enzyme called lactase that breaks the lactose down into monosaccharides. But not all enzymes end in ASE. There are major ones like trypsin or pepsin, those ones that are in our digestive tract, they don't end in ASE. So it's not a rule that's applied every single time, but it's used often to have the suffix ASE on an enzyme. Now, with this, we're going to look at this from the standpoint, we're definitely going to be talking about enzymes, but let's look at this from the standpoint of, well, can molecules break without enzymes? Can their bonds break, and can energy be released, or can bonds be made without any enzymes? Well, it can happen, and the collision theory addresses that. It states that chemical reactions can occur when these atoms and ions and molecules, when they collide with each other, and if there is a sufficient force of collision, these molecules, these ions and so forth, there will be a chemical reaction of some kind, either a catabolic one or an anabolic one. So, and as the name, it's kind of self-explanatory, they collide. Activation energy is the energy needed to disrupt stable electronic configurations. And so if in order to break a bond, which remember, bonds form because of the sharing or transferring of electrons. So in order to break that bond, there needs to be a certain amount of activation energy to activate it. Once the activation energy level is reached, that bond will break. The reaction rate is the frequency of collisions with enough energy to bring about a reaction. And reaction rate, you can use enzymes, which we'll talk about, or you can increase temperature, pressure. So you increase temperature, that's going to increase the speed of the molecules and the rate at which they're slamming into each other. So higher temperatures will lead to increased reaction rate. Lower temperatures will decrease the reaction rate because overall molecular motion is slowing down. Pressure does the same thing. When you increase pressure, you increase temperature, you increase the speed of the molecules. This creates more friction, that increases the temperature, so it's kind of an ongoing process. But the key thing I want you to get from this is the activation energy. The energy that's needed in order to disrupt electron configurations and break bonds, or also to build things up again as well. But typically, we talk about these in terms of catabolic reactions, or ones that break. So enzymes, I'd mentioned, they are involved intricately in these chemical reactions that occur within cells. So if you look at this graph here, and it's an important one. It helps you understand. You see it in just about every single biology textbook. When you get into microbial metabolism, you're going to see a graph that looks very similar to this. If you Google like enzymes and activation energy graph, this is the one you're going to see in some form. So you start with the reactants on the left, reactants A and B. And you'll notice, follow the black line on the graph. You'll notice that it goes up and it goes up to that green dash line. That's the activation energy level that is necessary you have to reach that level in order for A, B to break into the products A and B. And then it goes up, and once you reach it, it inevitably will then break, the bonds break, and you end up with the products A and B separate. If you look at the red line, though, the red line is showing the reaction with an enzyme. Notice the green dash lines. When the enzyme is present, the activation energy level is much lower. So not as much energy is required in order to break the bond when an enzyme is present. This is absolutely vital for life. Because activation energy, the level that's needed to be met to break these bonds or to build things up, that activation energy level is way too high. Like, for example, the temperature would be way too high in order for an organism to actually survive. Because the temperature level would have to get to, say, like 400 degrees Fahrenheit in order for these compounds to break. And of course, that's way above the boiling point of water, and that makes life absurd. You can't have life at 400 degrees Fahrenheit. So what do enzymes do? They say, come here, activation energy level, step it down about 100 notches. And so the enzymes bring that activation energy level way down to the point where life can actually exist. So without enzymes, you ain't got life. You got to have enzymes in order for a cell to actually live. Any cell, prokaryotic cell, eukaryotic cell, bacteria, humans, and everything in between. Enzymes are absolutely essential for these reactions to occur. And without them, the reactions won't occur, compounds don't get broken down, chemical reactions never occur, and then a cell can't exist because that's what all cells are based upon, the chemical reactions that occur within them. And enzymes are integral in this process. They lower the activation energy so that chemical reactions can occur within the bounds of life. So what are they? They're biological catalysts. Okay, you got the biological part. I think you understand that. It's organic. They're based on living things. Now, enzymes are not alive, but you get the point. They come from living things. And they're catalysts. So what's a catalyst? It's something that speeds up a chemical reaction without entering the chemical reaction itself. And that's important because enzymes are integral in chemical reactions, but they actually don't become part of the chemical reaction. They're not used up for the chemical reaction. And enzymes often are specific for a chemical reaction. One enzyme, one chemical reaction. Now, there are some enzymes that carry out a variety of chemical reactions, but that's not the rule. That's not the norm. Typically, you have one enzyme for one chemical reaction, so there's a high level of specificity. They lower the activation energy, and I already explained that in the last slide. You got to get the reaction started. Once the activation energy level is reached, the reaction will then just fall. It'll go the whole way to completion. It's not like you hit the activation energy level and then the reaction kind of sputters along and then it quits. Nope, once that level is reached, the reaction will conclude. The products then will result. Some enzyme anatomy, the apoenzyme, it's a protein component of an enzyme, so it's mostly a protein, but there is also a non-protein component of an enzyme as well. And typically those would be those four elements: iron, zinc, magnesium, calcium. Or it could be an organic cofactor, and we call that a coenzyme. And so vitamins typically function that way, where you have, say, like B vitamins, they're involved big time in metabolism. And so what happens is B vitamins enter these chemical reactions. They themselves are all part of another chemical reaction. They get broken down. They then hook up with an enzyme, and they actually become integrated within the enzyme, and then they serve as the coenzyme. The B family of vitamins, that's just one example of many, but that's how they function. They actually become integrated into the enzyme and function along with it. And without the coenzyme, the enzyme cannot function. So the apoenzyme it's non-functional without the cofactor. And like I said, they're all cofactors, and then but if it's an organic cofactor, we call it a coenzyme. So it's a kind of a specific cofactor. And then the holoenzyme is a whole active enzyme. It's the apoenzyme and its cofactor together. So here with these very simple, they look like Duplo blocks. It's like preschool building blocks or something. You've got this chunk here on the left that's got bits taken out of it. You add the coenzyme in the middle, and then you get this region that has a very specific shape, and then you can see the substrate fits in there rather nicely. Very, very simplified picture, but hey, it makes sense. It kind of works, I guess. And this is typically how it functions. Now, what this looks like is the enzyme binds to the substrate at the active site. That's that region, that pocket, that is specific to the substrate. And the substrate is the compound that the enzyme reacts upon. The compound that gets broken, for example, in this case, this is showing a catabolic process. Then you have what's called the enzyme substrate complex, where they're joined together very briefly. The substrate is transformed in some way. A bond is broken or it's rearranged or something. Enzymes can do this. They do a variety of things. It's not just break a bond, see you later. Sometimes the substrate, its molecules are rearranged by the enzyme, and then it gets released. And the enzyme then is recycled. The turnover number is about 1 to 10,000 molecules per second on average. However, there are some overachievers where their turnover rate is about 100,000 molecules per second. So that's mind-boggling how quickly they can actually work. So again, the substrate without the enzyme would never break into these products. at the temperature of life. You'd have to have a temperature way higher. Some other factor would be necessary to break it. Well, the enzyme says, "Don't worry, I got this," and it takes care of all of it, and our cells then can continue to survive, and we can continue to live as a result of the enzymatic work. One thing I wanted to say is, if you, let me go back to this slide. You'll notice that the substrate and the active site, they have kind of a complementary shape here, where one fits into the other one. There are two analogies that you will hear associated with this: the lock and the key analogy, where the substrate is like the key and the active site is analogized to be a lock. So the key goes into the lock and it fits, it's precise. Well, that was kind of the older view of it. In the 1950s, late 1950s, a new view came out called the Induced Fit, which explains it a little bit better. It's like lock and key, but better. So yeah, you got a specific substrate for a specific active site. It's like a hand and glove fit. But what happens is the substrate changes its atomic structure ever so slightly as it gets closer to the active site. And the active site does the same thing. It changes its atomic structure ever so slightly so that the fit becomes forced. And that's what induced means. You think of induced labor, for example. A woman is forced to give birth because of the application of a synthetic hormone, for example. That's what happens here with the induced fit. You have the substrate and the active site being forced together because of as they get closer and closer to each other, their shape actually changes ever so slightly to achieve the best possible fit. So lock and key is good, but it didn't account for everything that could actually happen within an enzyme and a substrate. What was going on at the active site is so precise, and so a more revised version came out in the late 1950s called the Induced Fit. So lock and key became, and more the new and improved version, it became the Induced Fit model. Enzymes can be denatured, and that's what this picture is showing here. You've got an active functional enzyme there on the left. It's got a very specific shape. Something changes it because of some kind of extremity in temperature, pressure, or pH, and we have what we call a denatured protein. So if you remember in the discussion back in Chapter 2 on chemistry, there are 4 levels of protein structure. Well, enzymes are at the 4th level. They're at the quaternary level of structure, the most complex and complicated one. And it's very tightly coiled up helices, and there's folds in it, and there's twists, turns, bends, and there's a couple of them joined together, and they're held together very tightly in a very specific shape. Well, you increase the temperature too much, you're going to break the bonds that are holding all these twists and turns and bends together. Those bonds break, and then it just unravels. As you see, and this just looks like an unraveled ribbon, and that's kind of what happens to them. And when the active site changes, it's over. If you don't have an active site that can conform to the substrate, if it doesn't match, if it's not complementary, then the substrate never gets dealt with, and the reaction never occurs. And if it's a vital process, which in many cases it will be, then there's no cellular process that occurs, and the cell can die. So denaturation is bad news for an enzyme. So anytime these extremes are present, enzymes can become denatured. We don't say they're killed because they're not living. They're proteins. They're not living things, so we don't say it's killed, but it's kind of like it's killed. It's just done. It can't do anything. It's just a chain of amino acids now with no specific function. These graphs are just showing that you can reach an optimal temperature and an optimal pressure here. So they will peak at a particular temperature, or peak at a particular pH, or whatever. The substrate concentration will increase enzymatic activity as well. However, substrate concentration can reach a point of saturation. In other words, the enzyme can only deal with so many substrates. So if you increase substrate concentration, that does increase the enzyme's efficiency, or its rate of reaction, but only up to a point, and that point we call the point of saturation. Vitamins can assist with this. Vitamins can enhance or they kind of like attract chemically substrates to enzymes, and so they increase the efficiency of enzymes. So take your vitamins; they're very helpful, not just as enzyme cofactors, as a coenzyme, but also as kind of like a substrate shepherd. They're like leading the flock to the enzymes, and then the enzymes can get their substrates much more quickly and then work more efficiently. Okay, there are a couple of types of what's called inhibition. There's competitive inhibition and there's non-competitive inhibition. We'll look at competitive first. This is when an imposter occupies the active site. And this can be reversible or irreversible, where the imposter remains in the active site, and that's as good as just denaturing the enzyme. I mean, it results in the same effect. There's nothing going to happen. If the active site is jammed up, the substrate can never get into it, and so the enzyme can't perform its function. Even though it's not denatured, it's got something jamming up the works in the active site. This greatly slows enzymatic performance if it's a reversible one, if the competitive inhibitor can be booted out. And I say, well, how can it be booted out? Well, maybe they're the same charge, and so because of the like charges repelling, the competitive inhibitor can be rejected or ejected out of the active site. They can be overcome by competitive inhibition can be overcome by increasing substrate concentration. So more substrates there, less opportunity for the competitive inhibitor to get into the active site, because there are so many substrates there, and so they just keep getting in. The competitive inhibitor gets frustrated. I want to get in there, but it can't because there's so many substrates that are there. So increasing substrate concentration can overcome competitive inhibition. Sulfanilamide, this is just an example of a competitive inhibitor. It's a sulfur-based drug that inhibits the bacterial enzymes whose normal substrate is PABA, which is just an abbreviation for a chemical compound. That chemical compound, PABA, is necessary to make folic acid, and if bacteria don't have folic acid, they shut down. So we slow down the enzyme, we kill the bacteria. So sulfanilamide becomes an antibiotic then, and it's jamming up the enzyme that's necessary to carry out bacterial metabolism. So we talk about antibiotics tearing apart the cell wall, breaking down peptidoglycan and so forth, which they do. Antibiotics, that's their number one target, is the cell wall. But we've also developed another class of antibiotics, whenever we understood how enzymes work, that enter the active site of bacterial enzymes, jam them up, slow them down, kill the bacteria. So this becomes an alternative antibiotic. And we need them. We need more alternatives of antibiotics because bacteria are becoming increasingly antibiotic resistant. So this is one example of a competitive inhibitor. It's competing with the substrate. And if you get enough of it, you're going to outcompete the substrate and you're going to slow down enzymatic performance to the point where it can kill the cell. Non-competitive inhibition. So now we don't have anything that's competing, and it sounds so nice and everybody gets along. It's non-competitive. It's a beautiful thing, but no, it's not at all. Non-competitive inhibition, a compound binds to another part of the enzyme, and that other part is called the allosteric site. And in fact, that's what allosteric means. It means another place. So there's another spot in the enzyme. Somewhere on the enzyme surface, and there are pockets all through it because it's a very complex structure, and so there's pockets all through the enzyme. Well, these non-competitive inhibitors can bind and attach themselves to these allosteric sites and become integrated into the enzyme. And when it does that, it shifts the shape of the enzyme. It slightly denatures it. And a slight denaturation, that's all that's required in order to alter the active site. When the active site is altered, the key can no longer go into the lock. The hand can no longer go into the glove. It doesn't fit. And so now the substrate just is rejected. It can't get into that active site. So the enzyme becomes basically useless and shut down because it cannot accept the substrate. This non-competitive inhibition can be permanent or it can be temporary. So in some cases, it's kind of like with competitive inhibition. It can be reversible or irreversible. An example is Tamiflu. I don't know if you've ever heard of this or have used it. I have in my family, and trust me, it works. If you have to take it early enough. So somebody in your family gets the flu. Okay, it's too late for them. They show signs and symptoms of the flu. It's over. You're going to have to rely on the immune system to take care of it. But family members who are around the sick person can get Tamiflu before they show signs or symptoms. So this will be at the very early, they might be at the very early stages of the illness. And as long as the viral number is low enough, Tamiflu can be effective. And what it does is it binds to an enzyme on the flu virus called neuraminidase. And what happens is the Tamiflu attaches itself, so it goes into your cells, mainly of your respiratory tract. There's binding sites there. So Tamiflu enters your cells, and then while the flu viruses are within the cell, multiplying and dividing, the Tamiflu attaches to the neuraminidase. And as a result, those viruses now cannot get out of the cell. And they can then never mature and leave the cell and go and infect other cells. And so it gives white blood cells a chance to phagocytize these cells that are full of these viruses that can't get out of the cell, and so that greatly reduces their number. So they never get the chance to infect other cells, and then they multiply and divide, and they multiply and divide. I mean, one cell can release millions of flu viruses, which will go and infect other cells. So if we can stop them before they exit the cell, you can slow and eventually then stop the progression of the illness. So Tamiflu works well. I mean, at least in our experience in my family, where we have utilized it. It's expensive, but it works. I think it's probably better than coming down with the flu. So Tamiflu, non-competitive inhibitor. There's another one as well, starts with an R. Oh, I can't remember the name of it, but it too is a non-competitive inhibitor, and it works in a different way than Tamiflu does. So I'm going to end there for part 1. And again, this is a 3-part series, so stay tuned for parts 2 and 3. And thank you for watching.